Hello? Okay. Oh, okay. No, not nervous. No.
I would want you to give this speech to my guys in Manila.
בבקשה. אדרבה, they can watch it. But Abadafka can't use any Hebrew words. I can't use Hebrew words. No, because it's like going on YouTube, and I'm going to put it.
Yeah, because even though it's a private channel, which means you have to have the URL to get in. It's not. I don't think it's.
No, I think they put it on YouTube.
Because YouTube, if you have the URL, you can find it. If you search for it, I don't know. That's that.
I see them very similar. Going back to C# Python.
Ready?
Start?
Yeah.
Let me just grab this for a second. I'll make it little. Hi. Good evening. Thank you, thank you. There's more seats up here, and if we need more chairs, we can pull chairs out of the kitchen. But there's plenty of seats up over here.
I don't want to stop anybody from eating.
Yeah. Or drink. All right, welcome everybody. Thank you for coming to our Lakewood meetup. It's everybody coming who continues to make this thing the success that it is. Tonight we have the honor of hearing from Professor Nasayanevsky regarding algorithms. Then I think, based on the last speech, I think you'll learn a few.
You have to stay all the way to the end to hear about the money. It's the last slide.
All right. So without further ado, we'll get started. Thank you.
First, I wanted to thank the organizers. I also want to apologize because I was supposed to give this talk like 6 months ago, and my beloved mother-in-law got sick. Whatever, it was a whole thing. But anyways, I apologize, and somebody took over instead of me, and I want to thank them. I also want to thank my brother-in-law, Elio, for being the intermediary, and my other brother, Zevi Hirschfeld, one of the richest people in Lakewood, who's going to give you the $1 million. Right. Anyways, so the name of the thing is called Algorithmic Gems. I think my brother-in-law made it up. I teach a class called Analysis of Algorithms. Okay, in college, and in Brooklyn College, and it's what's called the capstone class. It's the last class. It's the highest class, and it has some beautiful ideas that I want to show you. Some of these ideas. Now, I suspect that about a third of what I'm going to show you, you've already seen, but consider this talk to be an advertisement to get you to want to learn algorithms. Okay, what algorithms are all about. I also want to say, when you go for an interview, they're not going to ask you a question in how do you do this and this in C#. They're going to ask you a question in algorithms. If it's a big company, they're going to ask you an algorithms question, because C# is hot now, but in 2 years you're going to have J#, and then you're going to have this and you have that. These things come and go as time goes on. When I started computers, my father gave me a book called Using Basic. I was 12. Then I went to college. I did PL1, Pascal. All these things come and they go. Okay, but algorithms, I'm going to show you algorithms that are hundreds of years old. They're still important. Okay, so I'll continue the advertisement as we go on. So let's just read. Analysis of algorithms is one of the most important parts of computer science and software development. It compares various ways of solving computer problems. We will look at several simple computer problems and discuss clever ways of solving these problems. And they're simple things. This is the amazing part of the subject. I can explain these problems to an 8th grader and ask them how would you solve this problem? And you don't need to know anything. You don't need to know Bitcoin, anything. Basic questions. Okay. We will also discuss the hardest problems in computers, the P equals NP problem. We will finish by telling a way of making $6 million just by programming one problem. Okay. You might only be able to make $1 million, but for sure between 1 and 6. It's either 1 or 6. You're not going to get. I'll show you why. Okay. Okay. So first, I'm going to say why we study algorithms. Then we're going to go through a few easy problems to show you them. Then we're going to talk about some harder problems, and then we'll talk about the P is equal to NP problem. That's what we're going. Okay, so why study algorithms? First of all, it's practical. It'll make your life better. Okay, you'll see why. I mean, just knowing how to solve certain things is just a better way to do it. Second of all, it's common knowledge amongst programmers. Okay, it is. You're working in an office. They all know. They all might have. They probably took analysis of algorithm class. You have to know analysis of algorithms. They can banter around. I go to my brother-in-law. We banter around different questions back and forth. How do you do this? How do you do that? Okay. I brought 3 algorithms books to just show you what they are. Okay. This is the book. The book. Okay, it's called Corman, License, and Rivest, CLRS. When different programmers talk to each other, they just say, oh, how do you do this? Oh, CLRS 16.2, chapter 16, section 2. This has everything, okay? It's 1,280 pages. It's got some heavy math, but you got to learn how to ignore the math, but it has all the best ideas possible. Now, I brought 2 other books which were written kind of in opposition to that book because this is so dominant and everybody uses this book. These 2 books were written to be easier, to be more pictures, more friendly, et cetera, and they're good. They're good books, but this is the book. Okay, I just want to tell you, if you go on Amazon.com, this book has 60 reviews, this book has 7 reviews, and this book has 660 reviews. So everybody uses this book. Okay. Anyways, I'm just going to pass them around just so you take pictures. This book, I wrote a blurb on the back, so I had to read through it from cover to cover, and it's a very good book. It came out 2017. It's not really used. This is a 3rd edition, written by 3 MIT professors, and so it's used all over. Okay. Okay, so again, continuing with the advertisement. So it's common knowledge. Everybody knows these things, and everybody, it's part of the computer science or the computer culture. Okay, next, they're clever ideas. I told you what the problems we're going to work with. You can tell it to an 8th grader, and the solutions, you'll never get it. Okay, it's just really, really clever idea, and more so. In computers and math and everything, there's fads, okay? Oh, you got to learn this thing, and you got to do this, and you got to do this system, and this is the hot system, and 2 years from now, this is not the hot system, and tight pants is the hot thing, and in 2 years, fat pants are going to be the hot thing, whatever. In algorithms, it doesn't go like that, okay? Because, like I said, it's something that's been around for a long time. If you come up with a better algorithm to do this and this, I don't care if you're pink, yellow, white, whatever, you're getting your name in that book. Okay, if you come up with there's objective ways of how to measure things. Is it a better algorithm because it's this? Or a better algorithm because of that? If you come up with a better algorithm, you're in it. You get in the book, whatever. It's just the best ideas are taught in these things. And the last reason is complexity is important. So we all work with these fast computers, the Apples and whatever, and they do a million operations in a second. And you don't really think about how fast it takes to do this algorithm. Okay, but I'm going to show you an example where it does show up, and I'd like to. And again, we're going to spend a lot of time worrying about how do you do this, how long will it take. So these are important issues. Okay, so let's take two things. When I teach this class, I teach 6 different sorting algorithms. Well, I used to say, what do you need 6 different sorting algorithms? Just press the sort button, that's it. Okay, but I want to show you why it makes a difference. Okay, so I'm not going to go through these algorithms, I just want to talk about each one of them. There's selection sort and quick sort. Okay, selection sort is easy to program. It's a loop within a loop, a nested loop, easy to program. As opposed to that, quick sort is recursion, and it's not easy to program. It takes a little time to think about it. It's a 5-line program, but it's not easy to see it. This is a 6-line program. Okay, anyways, this is the only math you're going to see, so calm down. Selection sort is an n-squared algorithm. In other words, n times n. Okay, it depends how much work is done, it depends on how many people you have, but it's an n-squared algorithm. As opposed to this, quicksort is n times log of n. Log of n is a number a lot smaller than n, so n times log of n is a lot smaller than n times n. Okay, which means that this is a lot quicker than that. Great. So for n is equal to 1,000, 1,000 squared is going to be 1,000,000 operations. You're going to have to do 1,000,000 operations to sort a list of 1,000. As opposed to that, log of 1,000 is about 10, a little bit less than 10. And so n times that, so this will be 1,000,000 comparisons, and this will be 10,000 comparisons. Now, for a computer like this, which can do 1,000,000 operations in a second, this will take about a second, and this will take about 2/100ths, a hundredth of a second. It doesn't really matter to you. But let's try n is equal to 4,000,000. So for example, the Brooklyn telephone book. Boys and girls, there used to be something called a Brooklyn telephone book. Okay, before Google, we had things called a Brooklyn telephone book. You sat on it when you were small. It was a very helpful thing. It has 4,000,000 names in it. Okay, so let's look at the difference between 4,000,000 squared and that. Well, it's very simple. 4,000,000 squared is 16 trillion operations. 16 trillion operations. As opposed to that, this would be 88 million operations. 88 million operations is 88 seconds, which is about 1.5 minutes. This is a couple of weeks. Okay, a couple of weeks at least. Okay, so it does make a difference. Again, you're sorting the Brooklyn telephone book. Well, it's already sorted, but sorted by number. Okay, inverse sorted. Sorted by number. It would, if you do it with this algorithm, it would take you a couple of weeks. As opposed to this will take you 1.5 minutes. But bubble sort is worse. Okay, bubble sort is worse. Okay, okay. Now, it's not only complexity. You might say, okay, look. Quicksort is so much better. Why do you even need selection sort? So 2 reasons. 1, it's easy to teach. Okay, like bubble sort, it's easy to teach. It's the first thing to teach. But more importantly, it's good with almost sorted data. For example, let's say you have Brooklyn telephone book and you're trying to sort it. Okay, but you add in, let's say, there's 4,000,000 people in Brooklyn. 10,000 people moved in. Yes, there are people that still move into Brooklyn. Most move to Lakewood, but there are still people moving into Brooklyn. So when you want to sort that, okay, it turns out selection sort is much better than quick sort at sorting something that's almost sorted. In other words, you have 4,000,000 sorted, then you add in 10,000 more, it's better to use selection sort. So again, this is the part of analysis of algorithm. Don't just learn the algorithm. You got to analyze when is this one good, when is that one good, et cetera, et cetera. Okay. Okay, so let's do some easy problems. Find the maximum and the minimum. So, for example, you have a set of numbers. You have an array of numbers. We're here an array. Actually, you're almost set up as an array. 2-dimensional array, 5 across, 20. Okay, you have an array of numbers. I want to find the oldest person and the youngest person in this room. Okay? Okay, so the maximum and the minimum. So how do you do it? Okay, so one way of doing it is very simple. You ready? Go through the room, call him max so far, right? That's the standard name of the thing. Call him max so far. Go through the room. Are you older than max so far? Are you older than max so far? Are you older than max? Go through the entire room. Find the oldest. And every time, if he's older than max so far, I make him the new max so far, and you go on to the end. How many comparisons does that take? Well, if I have n people in the room, I don't compare him to anybody. I consider him max so far, and then we go through it. And my brother-in-law, Zevi, is the oldest person in this room by far. Okay? That's why he did it. Okay, so the simple algorithm is as follows. And again, this is a question I can ask anybody. Simple algorithm. Find the max in n minus 1. Find the min in n minus 1 comparison. Just like you find the max so far, you can also make a variable called min so far. Go through the room. N minus 1 plus n minus 1 is 2n minus 2 comparisons. Done. Okay? Can you do better? Can you do better? And the answer is, well, here's a more advanced algorithm. Set up a max so far and a min so far. So take these two people and compare them. Just do one comparison, compare them. Okay? He's older than him. Okay, good. Now, I go to the next one and I say, okay, are you older than max so far? Okay, let's say he's max so far, he's min so far. Are you older than max so far? If he tells me yes, then I make him the new max so far, and I go on to the next person. I don't have to compare him to the min, because if he's older than max so far, I don't have to worry about the min. So I go to the next person. I ask him, are you older than max so far? If no, then I have to check, maybe he's younger than min so far, right? We're trying to find two things, the oldest and the youngest at the same time. So I would have to ask him two questions. And most people I would have to ask two questions. The oldest person, are you old, these two? I did one comparison for here, but for every other person I have to do, in the worst case, two comparisons. But a lot of times I'll only do one comparison. Are you older than max so far? If he is older than max so far, I don't have to worry about it anymore. Okay, I don't have to ask if he's younger. So here's the pseudocode for that. Oops. Set up a max so far and a min so far. Ask each, are you older than max so far? If yes, max so far is equal to the new. Okay, if no, ask, are you younger than min so far? If yes, then min so far is equal to the new. So again, we have set up one, and then for all the n minus 1 person, I either do one question or two questions. Okay, I either do one or two questions. Okay, 2n minus 2. The best case is if I only ask one question. How would it be if I only do one question? How would it be to ask only one question? Well, if things were in ascending order, like my brother-in-law over there is the oldest, if he's the youngest, and then every single person would be older as we go along. So you would always be bigger than max so far, you would be bigger than max so far, et cetera, et cetera. We would go to the oldest person. Then every person I'm only asking one question. Okay, so that would be a great case scenario. Then I would only have n minus 2 things. But on average, some people I ask one question, some people I ask two questions. So on average, I ask 1.5 questions for each person. Can I do better? And the answer is yes. So here's a clever way. You ready? Take these two. Ask who's the older, who's the younger. Okay, he's older, he's younger, he's max so far, he's min so far. Now I take the next two, okay, and I ask 3 questions to these two people. 1, who's older? Let's say he's older and he's younger. Okay, so I find out who's older. Then I take the older one and I compare him to max so far. Then I take the younger one and compare him to min so far. Make sense? Again, I found max so far, I found min so far. Take these two people, do 3 questions. 1, who's older? The older one I compare to the, if he's older than him, I don't have to compare him to the younger one, to the min so far. I compare him to the max so far, compare him to the min so far. It's right, it's 3 questions for every 2.
You have 5 questions for 4 people.
No, I have, forget about these 2. For every 2 people, I have 3 questions.
Max of 1.5, not average 1.5.
Right, it's the max. So in the worst case, I'm going to have 1.5.
Isn't that what you had before also?
No, I has on average. But this is, in the worst case, I'm going to ask every single person, every single pair of people, I'm going to ask 1.5 questions.
Maybe better or maybe worse. Before it was an average of 1.5 also.
Right, right.
Here you're guaranteed
Right, here I'm guaranteeing 1.5. But it's also the chances of it happening that it's less than, in other words, to get it so that it's less than 1.5, and the last thing is a little bit harder to set up the data. Okay, does everyone understand this? 3 questions for every 2 people is 1.5 question. Say again? No, because if he's older than him, right? I'm looking for the maximum and the min. So even if both of them are younger than min so far, but only one of them will be min so far. Right. Right? So yes, both of them can be younger than min so far, but I don't have to check both of them. Right? Okay, good. Okay, so I did a PowerPoint graphics without sound here, so watch this. I compare 2. He's the older, he's the younger, and then we compare the next 2, and no changes. And then we compare the next 2, and we say, okay, he's the older. And then we can compare the next 2. This is so cool. Okay? And finally, he could be younger, he could be older, et cetera, et cetera. Anyways, worst case, I have n over 2 pairs. 3 times n over 2 is 1.5 in the worst case scenario.
First pair, you only do one comparison.
Right, right. So you have to worry about that, right. Now also, what happens if you don't have an even number of elements here? Right? If right, right. No, but Zevi is the oldest. Okay, next. How do you find the maximum and the second maximum? Okay, so the runner-up. Again, simple questions. So let's do it. Find the maximum and the second maximum. This is a simple algorithm. Ready? Find the oldest person in the room, Zevi. Then go through the whole room and find the next guy who's the oldest person in the room. Okay? That's a brute force search, right? You go through the room twice. You want to find the maximum and the second maximum, so you do it. Okay, find the maximum n minus 1 comparison, find the second maximum n minus 2 comparison. That's 2n minus 3 comparisons. Okay, more advanced. Set up max so far and second max so far. Ask each. Okay, so again, I'm gonna ask these 2 who's older. He's gonna tell me he's older than him. Fine. Then I come to him and I say, are you older than max so far? Okay, here's the way to look at it. You ready? I set up these 2 as max so far and second max so far. Then I come up with a new person. I say, are you older than max so far? If he tells me yes, then he becomes second max, he becomes max, right? If he tells me no, then I still have another question to ask. What's my next question? Are you older than second max? Right? I'm looking, he's older, he's the second max, so I have to go over here and ask, are you older than second max? If he is, then he's still max, he's second max. Okay, and I got to do that for every single thing. So again, every single person I can ask 1 question, are you older than, or 2 questions. Are you older or are you somewhere in between? Okay, so again, we can go through that. Best case 2n minus 2, average case 1.5. Can I do better?
So this is identical to the max and min.
Right.
The max is
Right. You're basically brute force going through, but you're doing it 2 times.
You would do better if you start from the bottom.
Right. Okay. Right. So if he was the youngest person.
You're asking each person who's younger.
Oh no, that's the same thing. That's the same algorithm. I could ask. So I could say, are you younger than? Are you? I could start here and say, are you older than second max, and then go over there.
No, in most cases, once you hit, you'll end up with less than 1.
That's going to be 2n then, because if you ask the second guy, you might still be.
The way you set it up,
Right. Let's say I say, are you older than second max, and he says no. So then I only asked 1 question. Okay.
To knock out 2 possibilities in 1 question.
Right. Okay, but now let's do, okay, can you do it better? Okay, can we do better? Can we do better than this 1.5n? And again, this is not a hard question. This is not a hard topic. This is nothing. Every horse race works like this, whatever. Find the top 2 students in your class. Look at their grades, find the top 2 students in your class. Okay, so I got to tell you how it works better. So there was a man in Flatbush. This is a true story. There's a man in Flatbush. He was able to do the pin test. He died like 20 years ago. The pin test. Yeah. Yep. He was a friend of Hirschman, whatever. Um, he was a brilliant man, okay? And on the side, he played chess. And he used to walk around with a paper in the back of it. If I mentioned his name, you would know him. He used to walk around with the paper in his wallet. And it basically said that he, as a teenager, played Boris Spassky. Boris Spassky, I think, is still alive. He was the chess champion of the world, Russian chess champion of the world. And this guy was in Israel once, and he went to a chess game, and Boris Spassky was there, and he played him. And he told me, Boris Spassky is better than me. So he said, but I was the second best. Okay? He said, I can't fight. Boris Spassky is a better chess player than I am. Fischer? Fischer's an anti-Semite. Fischer's an anti-Semite. We don't like Fischer. Okay. Yeah, so that's where he belongs. Okay. So Boris Spassky. So that's Boris Spassky. That's very helpful. Okay, so I have to explain to you why my friend is justified for saying that. So I have to explain to you how a chess championship works. And basically, it's like in football and basketball. What is this called in basketball? March Madness, Sweet 16, something like that. Okay. So basically, I don't know these things. Basically, what happens is there's 162 plus 62, 124 people registered to go to a chess match. Okay, and this is what it looks like in the beginning. There's basically 64 tables sitting around. Okay, and everybody mills around, and you know, after a while, the judge says, "Okay, everyone sit down." It's like a Chavrusa tumult. Okay, and everyone sits down. Okay, and they play against each other, and the referees go up and down and to see if there's any problems, any discussions, any whatever. Everybody's quiet and everyone's playing. At the end, let's imagine that there are no draws. At the end, 64 people lose. They tell them, thank you very much, goodbye. Okay? They take out, they leave. The 64 winners stay. They take out 32 tables, and they have 32 tables left. And then those 64 people play against each other. And again, the losers leave, and the winners stay. Okay? And it goes on, 32, 16, 8, 4, the 4 top stay, and then finally 2 of the 4 players win, and then you have the final game. Okay, so let's just go back here. So 4 players play, and then the 2 winners play, and then the 2 winners play, and then you have the winner. Okay, now let's do that for numbers. Again, what we're looking is for the best player and the second best player. Okay, so here's the thing, and you can, as a human being, you can see this is the best player and this is the second best player. But rather than going through it, in order, let's do what's called a tournament method. Okay, so 5 and 7 play. 7 is bigger than 5. He's the winner. 17 and 18 play. 18 is the winner. 6 and 12. 12 is the winner. 13 and 15. 15 is the winner. Okay, 18 and 15, 18 wins here, 15 wins here, 18 plays, 18 is the winner. No problem, no doubt about it. However, the second best player is not 15. What do you have to do to be the second best player? What does it mean to be the second best player? Well, it means you're the best player except for one person, the best player. To be the second best player means you're the best player around except for one person, the best player. So how do you find the second best? And the answer is you have to search through the tree to see who won. Okay? So you compare, well, I do it. Compare 17, because 7 played 18, 17 played 18, 7 played 18, and 15 played 18. Now you have to go through these 3 things on the list, and see which is the maximum of those who lost to the winner. You understand? You go through the list, go through who lost to the winner. okay, and find the maximum of those who lost to the winner, okay, and that's 17, okay. So, just to go back to my friend, here's Boris Spassky. My friend just sat down on a chair, and all of a sudden he picks up his head, and there's Boris Spassky in the beginning of the tournament. He lost to him. He lost. He said Boris Spassky slaughtered him. He said, but I am the second best player of those 164, because you would have to go through all those lists to see who he is. And he said, I was better than them. I walked out of the tournament 10 minutes after I walked in, but I was better than all the rest. Okay? But now you can understand why. So then 17 would go up here, then 17 would go up here, and it would be. But still, you have to check all the losers. By the way, this is a very interesting thing to program. Okay, think about it, programming it in an array. You have to do every second one. You have to. No, please.
15 played more than one person and he won, and 18 and 17 lost right away.
No. Okay, so here we're just talking about numbers. So we're not talking about. Fine, 18 played 3 people. 18 was the only person who had to play 3 people.
And he won.
And he won.
He's the best.
No, he's the best because he's the best.
These are no bearing on the ranking. The ranking was from previous.
Right. Okay. Anyways, using the tournament method to find the best is n-1 comparisons. Doesn't help you. You have 1, 2, 3, 4, 5, 6, 7, 8. I have to do 7 comparisons. 1 comparison, 2 comparison, 3 comparison, 4, 5, 6, 7. Doesn't help you. However, to find the second best, all I have to do is climb this tree and see how many things I got. Okay? Just to keep you busy tonight while you're thinking, driving home, whatever. How would you do the second best, the second best, what is it called in horseback? The three best. Winner's circle. Best, second best, and third best.
Concentrate too hard while driving.
Right. Well, you're in Lakewood. You can't.
I disagree with this college grading.
Okay. It doesn't matter. You're in Lakewood. You can't drive anyways fast. You're in traffic. Okay.
Compare it to anybody that lost to the winner and anybody that lost to the second.
You have to compare both of them, right? Because the third best could be he played the second best, or could be he played the first best. Go. Oh.
In terms of efficiency, you're probably what's efficient in terms of the minimum amount of comparisons. But isn't there a cost of also going back and finding all the losers?
No. You need the right data structure to know how to put it in. What you have to do is you have to keep track of every loser. You have to keep track of every loser. So, for example, these guys have a fight. You don't know, maybe 7 is the winner. So you have to keep track of the loser. And it is a data structure that can do that. But, right. So it has other things that you have to worry about. Okay, so let's talk about this problem. So this guy, his name is Carl Friedrich Gauss. Anyways, he is considered till today the greatest mathematician who ever lived. So there's a story that goes on with this. Okay, and the story goes as follows. I'm not sure it's a true story, but it's a good story. The story goes as follows. When he was a 5-year-old kid, he wasn't behaving well. When he was a 5-year-old kid, he wasn't behaving well. So the teacher went over to him and said, "You, sit down, add up all the numbers from 1 to 10. Keep him busy." So he goes and he jumps up and he says 55. The teacher kicks him out of the office. Kicks him out, goodbye. Anyways, that night the teacher goes home, adds up all the numbers from 1 to 10, sees he's right. Okay? It is 55. Okay? The next day he's misbehaving again. Teacher tells him, "You, add up all the numbers from 1 to 100. 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay? And instead of adding them up, he just jumps up and says 5,050. Teacher kicks him out, sends him to the principal, et cetera, et cetera. Okay? She goes home, the teacher goes home, adds up all the numbers from 1 to 100. It works out exactly. Okay? Next day, he comes to class, he's misbehaving. She figures, okay, he memorized 10, he memorized 100. Next day she says, okay, add up all the numbers from 1 to 376. Okay? And without blinking, he jumps up and he gives the answer. Okay? Without blinking. Okay, as a 5-year-old kid. I'm not Gauss. Okay, anyways, so what was he doing? How did he do this? Okay? Okay, so here's the numbers from 1 to n. Okay, he wants to add up all the numbers. So again, me and you and Zevi would do it like this. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. Keep on going till you get to n. Okay? But Gauss understood the following rule that they teach in 5th grade. A plus B is equal to B plus A. Now what the hell does A plus B is equal to B plus A mean? What it means is you can add these numbers in any order that you want. Doesn't matter the order that you add numbers. Okay, you can add in this way, you can add in this way. Okay, so rather than adding them the way I would do it, 1 plus 2 plus 3 plus 5, he says 1 plus n. 1 plus n is n plus 1. Right? Nope. 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is n plus 1. 4 plus n minus 3 is n plus 1. Question, how many pairs do we have here? Answer, n over 2. Okay, so all you have to do is multiply. If you want to add up from 1 to n, all you have to do is multiply. You have n over 2 pairs, multiply it by n plus 1. So all you have to do is multiply n times n plus 1 divided by 2, and you add up all the numbers right away. Now, this is done in the 1770s, but this is an algorithms question. Look, I would have done it 1 plus 2 plus 3. I would have done it with n minus 1 additions, because there are n minus 1 plus signs over there. But Gauss, at the age of 5, realized that no, all you need is 1 multiplication, 1 addition, and 1 division. That's it. So 376, all you have to do is multiply 376 times 377 divided by 2, and you get your answer. That's a clever answer. Okay, rather than doing n minus 1 additions, he did 1 multiplication and 1 division. That's it, and an addition of 1.
141,751.
So there. Okay. Okay. One more easy problem. I'm sorry, when did we start? Oh, okay. Oh, well, okay. So I don't want to just do number things because that's boring. I want to tell you about a thing, a graph problem. So this is called the Königsberg Bridge problem. Königsberg is a city in Prussia. It was in Prussia. Okay, it's right next to Memel. Memel's where Sosalanta is buried. Okay, died. Anyways, and Königsberg had 7 bridges. There were 7 bridges in Königsberg. Okay. Here's a better graph, and people used to do the following trick. Oh, no, I'm sorry. People used to do the following puzzle. Okay, they would try on a Sunday afternoon to walk, start any place, walk across all 7 bridges exactly once. In other words, don't cross any bridge more than once. Okay, so you know, let's say you start here, you go across here, go there, don't. You can end up on the island. You can start at the island. I don't care where you start. I don't care. But I want you to go through every single bridge. By the way, how many bridges are in New York City? Say again? Take a guess. Yeah, you can name 7, right?
A better thing would be add up all the tolls.
No, because anyways, there are about 1,400 bridges in New York City. There are 1,400, but you can Google it yourself. Type in number of bridges in New York City. 1,400 bridges in New York City. Oh yeah, oh, Goethals, every one of them overrode us. It's a bridge over.
Including the boroughs, not just
Right. But look, I never forgave them for building the George Washington Bridge, which connects New York and New Jersey, but it's still there, you know, like, I can't. You can start anywhere you want. You just have to come back to where you started. Okay? Oh, I have no idea. Okay? So let's see if it's possible. So Catherine the Great, who lived in the same time, lived around that time, she decided to make Russia a better place. So she went to Germany and she invited some German mathematicians to come to Russia. One of the things she invited was a guy named Leonhard Euler. Okay, and she invited him to come to St. Petersburg to do it. And when she invited him, she told him over this thing that certain people in Königsberg try to do this, and she asked him, can it be done? Okay, so if Gauss was the greatest mathematician of all time, he was the second greatest. Okay, because they're still known. Okay, good. Anyways, so he said like this. He said very nicely. He said, look, let's say I'm in this part of town. By the way, this is not strange. This is not strange. New York is like this also, right? We have Manhattan, we have Staten Island, we have New Jersey, Nebuch, and we have New York. We have the only part of of the United States, the only part of New York that's part of the United States is Bronx. So we're thinking of seceding. Anyways, so this is not a strange setup. And again, it's near the water. You can't go to Königsberg now because it's a naval base. Because it has so much waterways, it's a naval base. Okay. Anyways, so he said, look, it doesn't matter if you start here and you go for ice cream and then you go here and then you cross this bridge and then you walk over here and then you check this out and you go shopping here and then you cross. He said, look, you might as well think of the land masses as a single point. Right? So crunch this landmass to a single point, crunch this landmass to a single point, crunch this landmass to a single point, crunch this landmass to a single point. And then I don't care how big the bridges are, how wide the bridges are, I just want a line from here to here. And so he invented this thing called graph theory, graphs. This is a graph. And this is a better way of describing the question. Here's the question. You have 4 land masses. You have 7 bridges, 1, 2, 3, 4, 5, 6, 7 bridges. And the question is like this. Given a graph, tell if there's a path that starts and finishes at the same vertex and crosses each edge exactly once. That's exactly what he wanted. You want to start in one place and finish in the same place. Go around, okay, hit every single edge, bridge exactly once, and come back to the original place. Question, is that doable? Okay, for this one, it's not. And we'll see why. This is called the Euler cycle problem. Cycle means you start and finish at the same place. Okay, Euler is the guy who invented the problem. Now, how about for this one? Okay, let me show you. Ready? Go around like this. Go around, whoops, like this, and then finish there. Ready? Let's do it again. Start here, go around like this, up, down, and finish there. That one's doable. Okay? How about that one? I wouldn't even attempt. Okay. But Euler was a very smart man, and yeah, that doesn't bother me. I'm allowed to be in that middle island many times. I'm just not allowed to touch more than one edge. The bridges are the things I'm trying to do. Okay, so Euler said as follows. He said, let's say you have a vertex here, and you have 1, 2, 3, 4, 5, 6, 7 things going. So he says like this. Let's say your middle, there's a giant graph here. I'm just focusing on one. You start here, and you go into one of them. Well, you can't use that again, and you're stuck here. Now you're going to go out. I don't care which one you go out, but you can't use that again, so you're out. Now you go in. You go in through here. Now you go out. Now you go in. Now you go out. Now you go in. Now you're stuck. You started outside of this landmass, and now you're stuck inside this landmass. He said that's no good. So he said the following rule. Conclusion. There will be an Euler cycle if every vertex has an even number of edges coming out of it. If you have an even number of edges, every time you go in, you're able to go out, then there's no problem whatsoever. Okay? So let's go through here. There's 1, 2, 3 things. That's an odd. I'm not going to be able to do it. 1, that's odd, that's odd, that's odd. Not going to be able to do it. How about this? 1, 2, 3, 4, even. 1, 2, 3, 4, 5, 6, even. 1, 2, 3, 4, even. 1, 2, 3, 4, even. That's doable. Okay? How about this? Well, it looks daunting, it looks scary, but the truth is I can do it. I can easily do it. How do I easily do it? Go through each vertex. I don't even have to count how many edges come out. All I have to do is parity check. Okay? See the number that is even or odd who come out. 1, 2, 3, 4, even. 1, 2, 3, 4, even. 1, 2, 3, 4, even. I think they're all even. Look at that. They're all 4. I don't know, but if I have to finish at a certain time, otherwise I don't get to take home the leftover food. So. Okay. Anyways, here's a bunch of other graphs. Okay. But now we have a trick of how to solve them. Okay. All I have to do is go through the graph, see how many things. 1, 2, 3, 4, 5. Oops. No Euler cycle here. Maybe this one does. 1, 2, 3, 4. Good. Maybe it doesn't. Have to go through it. We have a trick. We can do it. How about these? Well, we have a trick. We have an easy way of telling, give me any graph size 100 dots. I can tell you whether there is such a cycle or no cycle. Good? Good. Okay, good. Let's talk about some harder problems. Given a graph, tell if there's a path that starts and finishes at the same vertex that crosses every vertex, every dot. Beforehand, we cared about crossing every bridge, every line. Now I want to cross every dot. Okay, so here's a nice example. Can you do it? Okay, and the answer here is yes. Look, watch. 1, 2, 3, 4. Come back. I don't have to cross every bridge. I could just cross the dots. So it's easy. How about there? Well, if I could do it here and you added extra bridges, for sure I can do it. Great. How about here? I have no idea. Okay, this is a lot more complicated. Okay, how about here? Well, here I could definitely do it. Watch. 1, 2, 3, 4. Come around. No problem. How about here? Start, go here, go here. Oh, look at that one works. How about here? This one is a little bit harder. I start from A, I come around, I go here, go there. I have to end up in A. I have to end up in A. Okay, I have to end up in A. Is it doable? Okay, how about these? Is it doable? Okay, you ready to learn the trick? I told you the trick about Euler. Euler was the one you have to cross every bridge, and I said an even number of bridges coming out of every dot, that does it. How about here? Ready for the trick? No, nothing to do with odd numbers. Because we had odd numbers, and I showed you it was doable.
Number of dots divided.
No. No, here. This has a 5 number of dots. This has 15 number of dots. This is 10 dots. Okay.
Someone knew the answer, they would be in the world.
Oh, okay. You want? Say again? Could be yes, could be no. Okay. You ready for the trick? I don't know the trick. I don't know the trick. You should have hired another guy to give the talk because I don't know the trick. Okay? And neither does any of these 4 guys know the trick. So there we go. So the only way to try to do it, to solve the problem, to tell whether or not there's such a cycle, is try all cycles. Okay? In other words, try every single possibility and see if you can go through every single possibility and see if you can get it. Okay? How many different possible routes are there? Yeah. So one dot. Yeah. Yeah. You're gonna get yourself caught into a little district. I promise you it's not going to work. That algorithm's not going to work. Okay, let's try another problem. Okay, and this problem is called the traveling salesman problem. I'm sure you've seen it before. If you didn't see it before, then what's I told it to you once. You don't listen to me, so I don't care. Okay, a traveling salesman wants to visit some cities, and he wants to find the shortest path that hits every city exactly once. By the way, that's the Hamiltonian cycle problem, right? It hits every dot exactly once. Here we hit every city exactly once, but here we worry about something else. Here we worry about the distances. Before we weren't interested in distances. Here we have it. No,
Traveling salesman doesn't have to get back to the same point.
there's a difference between the traveling salesman problem and the traveling salesperson problem. I'm just kidding. The salesman doesn't want to come home, but the salesperson is a proper feminist. They want to come home. Okay. Okay. So here's a typical graph. Okay, and it has the distances. In question, I want to know, how do I hit these 6 cities? Okay, that hit every single city. Come back to the original one. What's the best way, the shortest possible way of doing it? Yeah. Okay, hold on. So, the simple way of doing it is try all 6 factorial possibilities. Try everything. By the way, it's not so hard. 6 factorial is 720. Okay, for 6 cities, you need to try, for the first city, you'll have 6 possibilities. For the second city, you'll have 5 possibilities. For the third city, you'll have 4 possibilities. There are 720 possible paths. For each possible path, what you do is you add up all the numbers, keep a running min so far. You're looking for the shortest. Min so far. Keep a running total, okay, and then go to the next one. Go to the next one. 720. This computer can do it in a second flat, less than a second flat, in a tenth of a second flat. Okay. Okay. For n cities, you have to check n factorial possibilities. N times n minus 1 times n minus 2 times n minus 3, et cetera, et cetera. For n is equal to 100, how long will it take? Okay, so let's just go through this. For 6 cities, I told you this computer can do it in less than a tenth of a second. How long will it take for 100 cities? Now, without taking out your cell phone. A year, a lot longer. A few years. Anybody else? No, yes, an exact. First of all, you have to go through it. Let's assume that this computer can do 1,000,000 routes in a second. That's a nice assumption. Okay, 1,000,000 routes in a second. How long will it take? Okay, let's go through it. Let's calculate 100 factorial. Remember, every time you multiply 100, you're adding 2 digits to the number. So that's 100 factorial. That's how many paths you have. If you have a computer that can check 1,000,000 paths in a second, then we need 100 factorial divided by 1,000,000. That's how many seconds. Okay, that's how many seconds. That's how many minutes. That's how many hours. That's how many days. That's how many years. Dividing by 365 gives you how many years. So it turns out to be 2.9 times 10 to the 142 centuries. Okay? Somebody here said a couple of years. Okay? By the way, that's the best possible answer I've gotten. Usually I get 2 weeks. 2 weeks. Okay? Okay? That's 2.9 times 10 to the 142 centuries to solve this problem. And notice, the problem is an objective problem. I want the shortest path. And I can make the problem a lot harder. Let's say I'm a typical traveling salesman, and I want to visit the 300 most populous cities in the United States. Okay? 300. I have to do 300 factorial. Okay? That's way, way bigger than 100 factorial. It's a lot harder. Okay? Anyways, this is an essential limitation of our ability to know. I wrote about this in this wonderful book, which you have to buy, called The Outer Limits of Reason. Doing it to the camera. Okay? Buy this book. It'll make you happier. It'll make me happier. Buy this book. Anyways, but we talk about these things that can't be known. That can't be known. And again, I'm not asking you to look at a picture and tell me, is the picture a pretty picture? I'm not asking you to do a moral action, subjective questions. I'm not asking you things like that. This is an objective question. What is the shortest path? Find me the shortest path. Good. Yes, absolutely. No? Oh, yes. For very easy cases, you could know it. Okay, hold on. Okay, responses to the traveling salesman problem. Whenever I teach this, I always get 4 responses. One response I'm not going to write. The one typical response is, oh, you're using your kind of computer. But if you used an Apple computer, then there would be no problem. Steve Jobs can do this. No problem whatsoever. Okay? That's one answer I usually get. 1 second. Okay. So, first of all, computers that go 10,000 times faster. Now I have to say that's not a strange thing. My beloved mother in 1983 bought me a TI-99 Radio Shack computer, okay, and I have it. It's under my bed in my mother's house, okay, and since 1983, computers have been going at least 10,000 times faster. So it's not a strange thing to ask for a computer that's going to go 10,000 times faster. You might say, oh, look, I can't solve it. It's going to take me a long time, but I'm going to get a computer. I'm going to wait 10 years, going to get a computer that works 10,000 times faster, and I promise you, computers in 10 years will go 10,000 times faster, okay? And well, no, he won't be able to do all the routes in 10 years, but okay. So if you do it like that, then it'll only take 2.9 times 10 to the 137 centuries. That's 1/10,000th of 10 to the 142 centuries. 1/10,000th. So the point is, that's not going to help you. Having a computer go 10,000 times faster is just not going to help you. How about what he said? How about splitting the problem up? I'm going to take the problem, I'm going to put it on the cloud. I sound sophisticated when I say that. I'm going to put it on the cloud. I'm going to have everybody use it in their downtime. I'm going to have everyone download the problem, a part of the problem. And yes, it's very, very, I just think about it. If I have 100 people in this room, I say, look, I want you to do all the problems that start in New York. I want you to do all the problems that start in Denver. Try, you know, I can split it easily like that. Right. Okay, so computers, how about computers with 10,000 processors? Okay, 10,000 processors. Okay, so it'll be 10 to the 133 centuries. That's 1/10,000. This is 1/10,000th of that.
Oh, you're saying and 10,000.
Yeah, let's say I have 10,000 times faster computers, and I do it on 10,000 times 10,000 processors like that.
Use the MapQuest API.
And well, it doesn't work. Okay,
Windows 10 computers.
doesn't help you.
Many monkeys jump.
Physicists tell us that there are 10 to the 80 particles in the universe. They can figure out how many particles are in a grain of sand, how many, you know, they can do a lot of mathematics, how many grains of sands are on Earth, how many planets there are, how many whatever, and they come to a number that 10 to the 80 particles in the universe. If every particle in the universe was a computer that's working on this problem, just 100 cities, it would still take 10 to the 62 centuries. Okay. Each particle is a computer. Okay. Okay. Next possible response. Somebody said it. Quantum computers. Okay. Now I wrote a book on quantum computers. Okay. It's the has the number one reviews in textbooks in quantum computers. I strongly recommend to buy it. Help me pay my mortgage. Buy this book. Okay. No. Yeah, I'm just trying to say, I'm trying to make a living here. I'm a traveling salesman. I had to come all the way to. My brother-in-law doesn't give me a pen. No, just kidding. Okay. Well, turns out quantum computers are not very helpful. In technical terms, quantum computers cannot solve an NP-complete problem. Okay, so all the buzz you hear about quantum computers is very nice. They will break RSA. They will break it eventually. But there is post-quantum computing, post-quantum cryptography. So that's very nice. Anyways, with a quantum computer, you only need 10 to the 71 centuries. Again, that's a lot faster than this and this, but still, it's not going to help your problem. What will help? What will help? Answer: better algorithm. What about a better algorithm? Heuristics. Find a better. Well, okay. So people have to solve these problems. For example, the traveling salesman problem is solved every day, badly, on a Brooklyn street. For example, a bus driver has to go to certain cities, certain stops, certain corners, drop off kids, pick up kids. Okay, and he wants to find the shortest route. How does he do it? Okay, and the answer is heuristics, intuition. He makes mistakes. He doesn't do it properly. Okay, but that is done. Okay, but what about getting the exact the best answer possible?
Use bees. I think they figured it out already. Seriously.
What? Using bees?
Yeah.
Yes.
Instinctively.
Yeah, okay. There has been a search for improved algorithms for almost 50 years to no avail. People have been looking for an algorithm for 50 years. It probably does not exist. I'm sorry, I'm not pushing you off. It's just these people want to know how to make $6 million, and you're holding them back. Okay, no one proved the better algorithm. Just like I don't have a better algorithm for the Hamiltonian cycle thing. Okay, you have to try all possible routes. So too, you have to try all possible routes. Brute force. I don't have a better algorithm. Finding a polynomial algorithm or proving that one exists would solve the P equals NP problem. Okay, so let's just talk about the P is equal to NP problem. Okay, so we've talked about two different things. We've talked about easy problems in the beginning, and then we talked about hard problems. Let's talk about it. So a trick where we go through the whole list and see what's there, what's not. Okay, as opposed to that, we have Hamiltonian cycle problem, traveling salesman problem. These are the hard problems. There are thousands of other combinatorial problems that are easy. There are thousands of other combinatorial problems that are hard. Just notice the Euler cycle problem, where you have to visit every bridge, that was easy. We have an easy way of doing it. The one where you have to visit every city, that's hard. Why is that? They're both the same problem. You want to start and finish in the same place. Okay, one you have to visit every city, one you have to visit everything. And why should one be extremely hard, take trillions of years, and the other one you could do in seconds flat? Okay, we call these easy problems, we call P problems. These we call NP problems. They're polynomial. NP stands for non-deterministic polynomial. It doesn't matter what it stands for. These can be done in polynomial, n log n squared, n to the fifth. By the way, just an interesting thing, there is not one algorithm in this book that's over n to the fifth. That's an interesting question. Why is it that the problems we come up with don't demand algorithms that take n to the sixth, n to the seventh, n to the eighth? I don't know. Okay. Problems that can be solved in exponential or factorial times. That's 2 to the n or n factorial. Okay, so these are the easy problems. These are the hard problems. The easy problems are a subset of the hard problems. In other words, if you can solve the problem in polynomial time, you can definitely solve it in exponential time. Okay? The P is equal to NP question is, we know that P is a subset of NP. Are they equal? What does it mean equal? It means this is a subset of this, but can this also be an element of this? In other words, is there an easy way to solve the hard problems? That's what it means to be a subset, that NP should be a subset of P. Is there an easy way, take a hard problem, is there an easy way to solve that problem? In other words, can every NP problem really be done in polynomial time? In other words, is there an algorithm to solve the Hamiltonian cycle problem? Is there a nice algorithm to solve the traveling salesman problem? Okay, that's what the P is equal to NP question. In other words, are there better algorithms for the NP problems? I presented it. I told you I don't know of any better algorithms. Do they exist? I can tell you now nobody knows of them. Okay, it turns out many of these N problems are interconnected. This means that if there's a polynomial algorithm for one of them, then there's a polynomial algorithm for all of them. If you can just find me a nice algorithm to solve the traveling salesman problem, I'll find you a nice algorithm to solve all the other NP problems. This is called NP completeness. Right, not approximation algorithms, real algorithms that give you the exact solutions. Okay, so here's the two possibilities. I asked the question, is P equal to NP or not? If they're equal to it, then we write it like this. P is equal to NP. Those are the easy green problems. As opposed to that, this is the way people think it is. These are the hard problems. These are the harder problems. Okay, now, in order to make $1 million, you have to solve this problem. Okay, I'll explain to you why. To show that, now, I want to show you, not only am I telling you how to solve it, I'm going to start you off. Okay? You see, just for a good, to show that P is not equal to NP, in other words, the fact that there are hard problems and easy problems, all you have to do is show that pick an NP problem, right over there, pick something that's hard, not in polynomial time, like the traveling salesman problem or the Hamiltonian cycle problem. Pick a problem here and prove that it does not have a polynomial algorithm. Prove that there's no way of doing this easily. Now, I don't know how to do that. And no one else does either. If you have a problem, I can find a solution. How do you prove that no solution exists for something? It's trying to prove a negative. It's a very hard thing. Okay, it's a very hard thing. How do you show that no pink elephant exists in the world? If I show you a pink elephant, if I want to prove to you that a pink elephant exists, all I have to do is bring in a pink elephant here. Okay, no problem. To show you that no pink elephant exists, that's a very hard thing to do. I have to go through the whole world and convince you. We have to prove that this problem cannot be solved by any polynomial algorithm. We don't know how to quantify overall algorithms. I don't know how to say, oh, this can't be done. I can say, for all numbers n, the following is true. For all strings, the following is true. But how do I say for all algorithms, if it's a polynomial algorithm, it can't solve this problem?
But doesn't proving that it does, if we find that there's a polynomial problem that can
Okay,
solve the same as the NP problem, isn't that proving that they are?
hold on. So I'm trying to prove this. You're saying maybe this is not true, maybe this is true. Good.
Prove that, doesn't that disprove that?
Right, yes. So if you prove this, then this is false. If you prove this, then this is false. Okay, it's one of these two. I want to just give you from my gut, not my head, this is true. Okay, I can't prove it, but I just have a feeling, a deep feeling, and most people think it's true too. Okay, most researchers think that this is true. Okay, to show P is equal to NP, very simple. Find a polynomial algorithm for any of the many problems. I gave you two NP problems today, Hamiltonian cycle and traveling salesman problem. Go, because it takes n factorial.
With an algorithm they didn't think about before.
Oh.
Well, that would be solved.
Okay, right. You're absolutely right. I know of them as the only way I know how to solve them is n factorial. If you find them that there's a polynomial, you're done. You find a polynomial algorithm, then come to me. Show me the algorithm first. I want to find. We'll meet in a corner someplace and show me the algorithm first. Okay. Don't come armed. No, friends. What can I? Okay. Do not spend too much time on it, because a lot of people have spent a lot of time on it, and it doesn't really work. Okay, I just want to tell you how to make money on it. So we have two possibilities. No, Nobel Prize is something like $16,000. It's not a lot of money. So we're talking $1 million. So in the year 2000, this guy named Clay, who was a multimillionaire, he wanted to push math. And so he had the experts pick out 7 hardest problems in math. Okay, and these are the 7 hardest problems in math. And he said, if you solve any one of these, I will give you $1 million. Okay? He's a friend of my brother-in-law's. Okay? Anyways, 7 million. One of them is the P is equal to NP problem. Even though you say, oh, that's a computer problem, it's not a math problem. But it's considered so hard that the mathematician said, you know what, this is such an important problem, we're going to consider it one of ours. Okay? So here's these 7 problems. Anybody who solves them does it. Now, don't do number 6, the Poincaré conjecture, because it was done already. There's a guy named Grigory Perelman, and he solved the problem. So there's only 6 more problems left to do. Okay, don't do this. They offered him $1 million, but he said, we don't do math for money, and he didn't accept the money. Okay. Okay, I'm sure there's nobody here that was going to do Lishma like that. But anyways, so we now have 6 more problems to do. Okay? So if you solve the P is equal to NP problem, you make $1 million, $1 million. Okay? The Poincaré died in 1905. So it's at least as long as this. This is 150 years at least. This is actually the youngest problem. This is P is equal to NP is from 1970s.
Why? It's only because since computers were invented, people have never thought of it?
They thought of, Gödel thought of it, whatever. They thought of it, but they just never formulated it. There's hard problems. There was hard problems. There's not hard problems. But to state it as a problem, no one was able to do it. Okay? This one is a little bit, maybe this is also 1970s. Okay, so I told you how to make $1 million. Now let me tell you how to make $6 million. Okay? There's another NP problem. I gave you 2, Hamiltonian cycle problem, traveling salesman problem. I want to give you a third one. Given a true mathematical statement, find its proof. Okay, so take a statement of math, whatever, theorem, okay, and have the computer generate all possible proofs, and let's find a proof for this statement. Okay, these are called theorem provers. The only thing is, it takes an exponential amount of time to do. It takes a long time. Okay, this problem will take trillions of years for a simple math problem. Something like a plus b is equal to b plus a. It would take years and years and years to find that. Okay, great. However, if p is equal to, so this is an NP problem. If p is equal to NP, then it's easy to make a polynomial. So this is a hard problem. But if p was equal to NP, that means all the hard problems in NP can be done in polynomial time. Then it's easy to make a polynomial algorithm that will solve this problem in a few minutes. So if p was equal to NP, you can do this problem also. Not only would you be able to solve the Hamiltonian cycle problem, not only will you be able to solve the traveling salesman problem, you'll also be able to solve this proof finding problem. Okay, so after proving that p is equal to NP, make such an algorithm, then formulate the other 5 Millennial Prize statements. They're all math problems. They can be written as a mathematical statement. Okay, and use your algorithm to find their proofs. This will give you $1 million to find that p is equal to NP, and $5 more million for those other things. You get $6 million. And all I got was a sandwich from you guys. Thank you, thank you. Hey, I want my books back. No, I'm just kidding. Anyways, thank you very much.
You drew a blank.